G'day. I've recently bought some switching mode power supplies. They're all 36 volts. First I bought two of these, which are 540 watts, so 15 amps. And before I voided the warranty by breaking that seal and messing around inside of them, I checked that they produced 36 volts, and under load I ran them through this business here, which is a whole bunch of 12 volt 50 watt halogen light bulbs, and I can wire them every which way. So put three in series so I could run them at 36 volts, and yep, it worked under load. And then I could parallel up, I think, 3 sets of 3 or 4 sets of 3 to get it up to 13 amps. So it worked fine. Both of them did. So good. And then I started messing around. Then I bought two more of these, which are 10 amp jobs, 360 watts, but I only checked that they produce 36 volts. I didn't try them under load, and they don't work under load. So in order to work out what's going on, first I want to go back to this one and have a look. I'm doing the trick of putting a loop of wire through the transformer, and then you can monitor on the oscilloscope and see the waveforms, and hopefully by looking what one that works looks like, then I can try the same thing on these guys. So I'll just turn this one on. We'll get the oscilloscope happening, sitting across the winding. The other one of these, when I was fooling around, I ran it at full load while it was out of the case, so there was no heat sinks on the output transistors, and they promptly blew up. I've replaced them, but still doesn't work, so there's something else wrong as well. Haven't looked any further into that. Here's part of my fooling around for for driving it with pulse width modulation. I did a very short little video just showing that recently. This was just going to set it to about 37 volts, but yeah, doesn't matter. So, and I'm running it through this isolation transformer, which even works on its side. I don't need to do that just yet, but if I start sticking the oscilloscope on the nasty side of it, the high voltage, I'll need the isolation. So now I've got 6 light bulbs in series. Well, first we'll run it without any load. So looking at the oscilloscope and zooming in. Right, I'll turn it on. The fan is on the power supply is just idling low. Don't know if that shows up. 37 volts. Looks a bit blurry on the screen, but hopefully it's visible. And there's the waveform. It's pretty wonky just at idle. So if I give it just a 100 ohm load, which is what's that, 370 milliamps I think, the fan speed increases, and you can see the waveform on the oscilloscope starting to look a bit more like a couple of square waves. And the frequency there is 26 kilohertz, by the way. Without the 100 ohms it's about 50, or yeah, the oscilloscope can't quite tell because it's such a mess. Now I'll turn on the 6 halogen bulbs, which will give us about 3 amps of load, and now we're getting proper square wave with dead time in between switching in each direction. And the bulbs are happening there, and it's drawing about 3 amps. With 6 in series it should only be drawing something like 700 milliamps, but because each bulb is now only seeing 6 volts, they haven't fully heated up, so they've got a low resistance, so they're drawing more current. I won't mess around trying to take the load further, but I just wanted to see that that's what it looks like under a little bit of load when the power supply is working properly. So now I'll do the same thing with one of these guys. One other thing, just while I still got this one set up, another thing I wanted to check was putting the winding just around the outside of the core rather than around the middle one there, which is much harder to thread the wires through. This is a lot easier to do. To get that one in, I have to pull the board out and mess around for quite a while. This was pretty easy. So I want to see if I can get the same waveforms just doing that, because if it's valid to do that, it's a lot easier. So let's look at the oscilloscope again. Looks pretty similar to before, and with the 100 ohm load, pretty similar. Haven't got the fan plugged in at the moment, so you can't hear that. The fan in that thing makes plenty of racket. And finally, the halogen bulbs. Oops, what am I doing there? Am I short circuiting it? No. What the hell's going on there? Oh, fucking idiot, I'm not putting it through the bulbs. Duh. Anyway, it stands with short circuits pretty well. It's similar looking, the waveform there. Jesus, that made a bang. Not exactly the same, but good enough to tell that the thing's operating. Certainly a lot easier to put the test winding on that way, so that's worth knowing. Okay, onto the other power supplies. Right, there's one of the 10 amp 360 watt jobs. Again, I've put in the wire and I've taken advantage of the fact that it can go just on the outside, much easier to thread through. And oscilloscope, and turn on the power to this guy, and 28 volts, why 28? Probably because I've been fooling with that adjustment. Let's wind that up to 36. Right, now if I put just this 100 ohm load on it, there it is at idle, and with the 100 ohm load it's starting to go into a square wave, so it looks similar to the other one. And I was sticking that on the positive, which is where I have to for this, but when I'm trying to run the lights I have to stick it on the negative. So I'll put it on that now, and it just dies in the arse. Runs out of volts completely. Going back down to here, connect the bulbs again. There's about an amp flowing, and I have, sometimes it will fire up. The lamps are on now and it's drawing 3 amps just like the other one does, and we've got a proper square wave up there, but usually not. Okay, well, once it decides to work, it keeps working. If I just let it wait a minute, try again. It's going to work for me now, little bastard. Trust me, it doesn't always work. It didn't work when I first tried it just before. Try the bulbs again. Yeah, see, dies in the arse. Try it again, and again, and it works. So there's something dodgy in there. Don't know what. I don't know much about these things. I'm learning, but so far not too much. So I think the next thing to do, okay, that's nice to look at on the oscilloscope. What I want to do now is check that chip for signals, make sure it's producing gate drive signals as it should to make these waveforms happen, but also check its inputs to its comparators and its dead time control, which is one way of disabling it. So some of the protection circuitry around it might be turning on that dead time control signal to shut down the supply if it thinks there's a short circuit or over voltage or something, or under voltage. So that's the next thing to try. And the nice thing about all of these supplies is that, right, any switch mode power supply's got its nasty side, which is mains in here, and then after it's rectified you've got 350 volts DC sitting here, and then to the switching transistors. So that's all nasty and not nice to connect to it, although because I've got the isolation transformer I can connect the ground of the oscilloscope to the negative of the high voltage DC and fool around it in there, but rather not. But the good thing about these ones is that the control circuit and all that stuff lives at the safe levels of the output. It's isolated, but it's it's not isolated. That is all connected to the output circuitry, and the isolation, well, you get isolation because of the transformer. Any switch mode power supply is going to do that, but a lot of them get the feedback isolation because you've got a connection from the output going back to the switching circuitry to make it regulate. A lot of them will use an optocoupler for that. So the control chip is sitting in the high voltage DC realm, and the only connection for the feedback is via an optocoupler. So all this stuff would normally be running at nasty levels, but in these particular ones you've got this gate, or not gate, base drive transformer So this circuitry here is sitting on the output, and the isolation between the control and the feedback into the switching is provided by this transformer here. So this chip drives a couple of these two little transistors down here, which drive the transformer. So all the nasty stuff's on that side of the transformer, and on this side it's all connected to the output, and it's relatively safe. So yeah, it makes it easier to fool around checking what's going on in that chip, which is the next thing to do. Okay, next day or a couple of days later, just to reiterate what's going on, 36 volts coming out of this thing, and we're looking at, on the oscilloscope, this one loop winding through the transformer. I'm going to put on a bunch of resistors as a load. It's about 1 amp at 36 volts, and you can see, I'll do it again in a minute closer up, but on the oscilloscope you can see the square wave starting to appear in the waveform. And if I use a much heavier load, 6 halogen bulbs in series, it shuts down. But obviously not catastrophically. It recovers as soon as I take the load away, and sometimes I can do that and it will actually stay on, but usually not. There's the 100 ohm, well, it's about 130 ohms. 100 ohms shuts it down, 130 doesn't. All right, let's have a look at a few signals on the controller chip. Okay, as I say, there's no obviously catastrophic failure going on. We'll just check the basics. Looking at the chip, there's voltage coming into it from the auxiliary winding. That goes to pin 12, and we're off the scales. This will run 1 volt per division, 50 volts per division. It's negative. What's going on there? Oh, you bloody idiot. Duh. Had the ground connected to the negative output, positive output. One moment, please. Right, ground probe connected to the right place. Go back to pin 12. We'll go to 10 volts per division. 9, 10, 11, 12. And we've got about 18 volts by the look of it. Let's go to 5 volts per division. There's ground, so 15, about 17 volts coming in, which is fine. And that chip produces a 5 volt reference signal, which is used in various places around the circuit. That comes out on the next pin, pin 13. And you can see 5 volts, go to 5 volts per division. Sorry, yeah, 1 volt per division. 1, 2, 3, 4, 5, nice 5 volt signal. Let's see if that gets disturbed by connecting that heavy load. Unaffected. Circuit shuts down, but the load doesn't stop the 5 volts appearing. So that's good, nice to know. Let's have a look at the gate outputs, gate drive outputs coming out of it. One of them's on pin 8. There's the gate drive. We're on 1 volt per division, so it's sitting about 2 volts and pulsing down to 2 volts, 2 and a bit volts there, or 2.28 actually, and the low is 320 millivolts. I don't like these other pulses here, these short ones, these runty pulses. I don't think they should be there. That was pin 11, which is the C2 output. If we go to the C1 output on pin 8, we've got the signals on the other peaks, on the positive peaks. We've got these drive signals, but there's also a little bit of that runty signal there, but it's not as bad as on this one. They're much more prominent. Don't like them, but anyway. But the most important signal, and the one I think is causing all our problems, is dead time control on pin 4. There's the dead time control. If we go to, it's on 1 volt per division. Let's go, let's leave it there. It's sitting on about, why isn't this showing us anything? Pretty steady voltage. You should be able to tell us what it is. Let's go to half a volt per division. On half a volt per division, and we've got about half a volt sitting on that TTC. Now, if I put on the light load, just the 130 ohms, which draws an amp, DTC isn't affected. See, there's a bit of noise on it. See the noise increases on there? But now if I put on the heavy load, it goes up to 5 and a bit volts. No, 2.5. And see how sometimes it actually stays there. Well, it takes a moment to drop away. Turn on, let it go. So watch the waveforms on the yellow trace, or green or whatever it is. If I take that away, you see the instant I let go, but about half a second later the DTC signal drops. So something going on there. That DTC signal, when it's high, it shuts the controller down almost completely. It shuts it down to providing just a 3% duty cycle, which is what those very narrow spikes on the transformer are. Let go of the short, put on the medium load. Actually, I'll leave the medium load connected and put on the heavy load. Once again, DTC goes high, it shuts down by going just a 3% duty cycle. Take off the heavy load. Aha, that's what I was hoping to show. See how it's latched, it's stayed on. A bit better than the 3% duty cycle. That's 3%, take the load off, increases a bit, but it's latched, it's stopped. And you can't see the voltmeter, but it's saying 7.8 volts. And the only way to clear it is to take off the minimum load. And now we're back to 36 volts again. Put the minimum load back, and it stays at 36 until we put the heavy load on. And then it latches again, and we're at 7.8 volts again. Take off the minimum load, and we're good. So something going on with DTC that's shutting this thing down. We'll have a closer look at that. Right, this is the circuitry around the DTC signal. There's the controller chip. Here's the auxiliary, that's the main transformer. This is the auxiliary power supply winding. We looked at that VCC and saw about 17 volts coming in, 5 volts coming out of the reference. Up here's the main power supply output, rectifier, filtering, blah blah blah, to there. Ground, VCC produces 5 volt reference to ground, relative to ground. And feeding DTC is the soft start circuit and the short circuit protection circuit. Now DTC is nuanced use. It's compared to the internal ramp signal of the chip, so you can control how much dead time between the output switching from one way to the other, but in this context it's not being used that way. It's simply low for enable the circuit, enable the power supply, and pulled high to disable the power supply. For soft start, that works by initially this capacitor here is discharged when it's turned off. When power is applied, it starts charging from reference, the 5 volts, through this resistor. Now, the capacitor, when it's discharged, appears as a short circuit, so what it's actually doing is pulling the dead time control up to 5 volts, so that makes the output of the thing inhibited, so it starts softly and charges up the output capacitors, not all of a sudden, but slowly. And as this capacitor charges up, this voltage here drops down 5 volts down to 0 volts or thereabouts, and the thing is fully enabled and power starts running. The short circuit protection works by monitoring the output of the power supply through this voltage divider. Now at 36 volts that will be producing 1.3 volts, which is enough to turn on this transistor Q5, which short circuits this capacitor. So there's no voltage in that capacitor, and because that's now at 0 volts, that diode prevents it doing anything to the dead time control. But if the voltage drops because of a short circuit, then this voltage will drop below what's required to turn on that transistor, and that happens at about 18 volts. This transistor no longer has enough volts on its base to stay on, and it lets go. So this capacitor here starts charging up via the Zener diode and this resistor, which I think is 100 ohms, but I'm colourblind, so my colour readings are probably wrong. But in any case, when that transistor is turned off, because of the voltage here dropping below enough to turn it on, this short circuit capacitor starts charging up. So this point goes from 0 volts up to sort of 5-ish. Bit dodgy the way they do that. Probably going to be about 10, isn't it? You've got 17 volts here and 6 volts there. It's going to charge up to 11. Anyway, the voltage across here increases until it's enough to go through this diode and start pulling the dead time control high. So it allows the short circuit to exist for a moment while this capacitor charges, and then the dead time control goes high and it disables the output of the power supply. So I think that is coming on inappropriately, and I want to look at the junction of that voltage divider, the input to the Q5, and see what sort of voltage we're getting on there. So back to the oscilloscope. Okay, looking at the junction of the two voltage divider going into the base of Q5, we're on 500 millivolts division, so we've got about 0.7 volts, which is a base emitter drop, one diode drop. If I put on the small load, no effect, but you see there's a bit of spiking on there. It's pretty quiet, it's got noise spikes on it. I'm talking about the cyan or white signal, whatever it is. As I say, I'm colourblind. If I put on the light load, it doesn't change the voltage because we're still getting 36 volts out, so that point should still stay the same, but we've got a bit of spiking going on. And if I leave that connected and then turn on the heavy load as well, it drops. So the transistor turns off, I'll let go, and it stays at bugger all because the thing's shut down. But it's in the latch condition. So I'm suspecting that that's not correct, that maybe those resistors are wrong, although if I read the colours properly it seems about right. It'll kick in at 18 volts, when the power supply drops to 18 volts, that will kick in, so that's okay. But I'm wondering if those spikes maybe are a source of problem. If we let's go to AC coupling on that. Crank up the volume and disconnect the light load so it returns to normal operation. You can see there's very large spikes. 100 millivolts division, so we've got spikes that are clearly going several hundred millivolts one way or the other. Turn on the light load again, and they're much stronger. Turn this down, so it's 200 millivolts per division. Let's go more, 500 millivolts division. So it's easily jumping half a volt in places. So I'm thinking those spikes might be causing the problem, because there are other versions of this circuit that I've seen where there's a capacitor across the base of that transistor on the short circuit protection. So maybe that capacitor should be there to absorb those spikes and stop a false triggering, which I think is what's happening. Some sort of false triggering going on. What do you reckon? Could that be it? I'm going to solder and the capacitor I've seen in the other circuits is 10 nanofarads. I'll solder something like that across that bottom resistor of the voltage divider onto the base of Q5 and see if that improves the tendency to shut down when it shouldn't. Right, I've crudely bolted a 47 nanofarad capacitor across that bottom resistor of the short circuit protection circuit, and now let's see if that has any effect. I'll connect the light load. Still a bit of spiking going on there. Okay, here's the big test. Turn on the heavy load, and she shut down again. Why? I think I'll pull the board out, check soldering connections, check components, measure the values. I want to check all the values of this thing, check the soldering on these components, measure these two resistors, check the transistor works obviously. Well, I've checked those resistors and this capacitor, they're all good. They are 39k and 1k5. The capacitor I thought I put across here, I put it in the wrong place. Now I'll put it there semi-permanently over here, and it makes no difference. So that doesn't solve the problem. I've also added this little bit of wire here, which is this point across the capacitor, and if I short that to ground so that the capacitor is always 0 volts, and then it doesn't matter whether this transistor is on or off, it's always as if things were normal, that is on. Doesn't matter if it goes off because of low voltage. And then try running things. Let's have a look at the oscilloscope. Okay, turn on my low load, and you see the picture squares up a little bit. If I connect the heavier load, you might be able to see that there's glow coming from the tubes, from the halogen lights, and we're getting a proper square wave there. So that was what was causing the problem. That thing is coming on when it shouldn't, that short circuit protection. I don't want to disable it, because it's there for a reason, but I might try fooling with these resistors to see if I can make it so that it has to be, well, significantly less than the 18 volts I think that it's coming in on. So yeah, so I'll fool around with those and see if I can improve things. Got a bit of trouble here with the winter sun, but we'll press on regardless. Yeah, so I'm playing with these values of these two resistors to determine the point at which a low enough voltage turns off this transistor and invokes the inhibit circuitry. And just to make sure that I was understanding it properly, I did a simulation to take account of the effect of the transistor. And yes, from 36 volts, the output is low, so it's not invoking the protection until about, there's 20, so 22 volts it starts to kick in, and by 18 volts it's fully on, and you know, it's inhibited at 18. So somewhere in that range, between 22 and 18 volts, it cuts out, which I'm pretty sure is too high. So to get an idea of what it should be, I looked at the 15 amp version of these things, you know, which is going to be essentially the same. They're both 36 volts, so the same cutout rule should apply, and simulated that, because that has 3K3 and 1K2, and there it cuts out at about 3 volts, so yeah, much different. So what I've done on this one, this power supply I got here, the 10 amp one, is change that to, I made it 3K9, could be 3K3 like this one, but 3K9 is probably pretty good. So I'm about to test it. The sun is a problem. Alright, turn it on. Nothing exploded, 36 volts. And I don't know if you can see that. Yeah, it should show up. I'm trying to block the sun. Yeah, same waveform there. Turn on the very low load, and we start to get a square wave there. Now if I try the heavy load, it shouldn't turn off. And it doesn't, and we're getting nice square waves over there. Right, and that's drawing about 3 amps. So I'm going to rewire this thing to draw closer to its 10 amp limit and see that it still works. And then I'll try shorting it out and see that the protection still works. I've rewired this so that instead of 6 in series, you've only got 3, and they're 12 volt bulbs, 3 of them in series, 36 volts should be right. So turn on power supply, 36 volts, connect this, and 3 bulbs come on, and it's drawing about 5 amps. Should be about 4 amps. 12 volts, 50 watts. Let's try increasing the load. If I take the other 3 which are still in series and put them in parallel with the first 3, look at the voltage. I'm blinded by these lights. Looks like about 6 amps, but the voltage has died in the arse. And in fact, if I go adding even more in parallel, but more in series in parallel with these 3, so if I put more in parallel, there's 3 in parallel with it, there's 4, 5, 6, 7, 8, and 9 in parallel with those first 3, and it's still too much for it. It looks like no matter what, we're only getting about 6 amps. This thing should be able to give me 10, but it's only giving me 6, which makes me wonder if there's not more resistors that are wrong. Just in that other schematic, there's the current sense resistor there, which is a big resistance wire link over here. Those 2 terminals go here. 2 resistors going into the error amplifier, and another one going up to the VREF. So that forms a voltage divider down to here. and the other side of that is being measured and compared in this error amplifier to turn on current limiting. So if one of these three resistors or more, one or more of them is wrong, just as this one was wrong, that would explain why we're getting such a low current. But then, these are cheap and nasty Chinese power supplies. They probably shouldn't be run at their maximum rated current limit, 10 amps. Should probably view this thing as maybe no more than 7.5 amp. Well, I should be able to get, say, 7.5 without losing voltage. So yeah, I should still investigate these resistors, but I don't know if I'll do it in this video. I wanted to use these in a project, and maybe I'll come back to that in some part 2 later. So for now, I think that will do. We've had a fix rather than a repair. Hope you enjoyed, hope you found it interesting, and I'll catch you later.